From the clean water that comes out of your tap to the smartphone in your hand, pretty much everything we use today has been touched, shaped, or moved by an industrial motor. They're these invisible giants, the hidden workhorses of our entire world. But how do they actually do what they do? Well, let's dive in and find out. So, if I were to ask you what powers the modern world, what would you say? You might think of giant power plants, or maybe the internet, right? But what if I told you the answer was something far more common, yet almost completely overlooked? It turns out the answer is millions upon millions of electric motors. These things consume over 40% of all the electricity on the planet, doing the heavy lifting for our entire economy. So in this explainer, we're going to break down how these absolutely essential machines work and how they're getting smarter every single day.
All right, first things first, let's get a handle on what these motors are and what they're for. They are, quite literally, the world's workhorses.
At its very core, an electric motor has one simple job: to turn electricity into motion. And it does this using a fundamental principle of physics, electromagnetism. See, when you pass an electric current through a wire that's sitting inside a magnetic field, it creates a force. If you harness that force just right, you get rotation. That's the magic right there. And you see this simple idea applied absolutely everywhere. Just picture a factory. You've got motors running the conveyor belts, powering the pumps that move liquids, spinning the fans for ventilation, and driving the compressors for air-powered tools. They are the muscle behind just about all of modern robotics and manufacturing. But here's the catch. The kind of force you need to haul a heavy conveyor belt is totally different from what you need to spin a little fan or to position a robotic arm with pinpoint precision. So, how can one type of motor do it all? Well, the short answer is it can't. And that brings us to the motor family tree. So let's take a look at the main branches of this family. When you get down to it, industrial motors are split into two big camps: AC motors for alternating current and DC motors for direct current. Now, what's really interesting here is the key difference between the two main AC types. On one side, you have the induction motor. This is the industry's go-to. It's tough, it's cheap, and it's reliable. Its claim to fame is that its rotor always spins just a little bit slower than the rotating magnetic field around it. That little difference is called slip. On the other side, you've got the synchronous motor. Its rotor gets its own magnetic field through a process called excitation. This lets it lock on and spin at the exact same speed as the field, which makes it perfect for jobs that need precise timing and top-notch efficiency. Now, over in the DC world, the big divide is all about brushes. Your classic brush DC motors are super simple and easy to control, but they have these physical brushes that make contact with the spinning part. And, well, they wear down, they create dust, they need maintenance. Brushless DC motors, or BLDC, solve that problem by using smart electronics to switch the magnetic field instead. This makes them way more reliable and efficient, but yeah, they are a bit more complex to control. Okay, so we have all these different types of motors. How in the world do engineers pick the right one for the right job? This is where the theory hits the factory floor. Let's take a really common industrial challenge: a big ventilation fan in a factory. It has to run reliably all day, every day. But the thing is, the amount of air you need changes. Sometimes you need it blasting at full power, and other times you just need a gentle breeze. And the key to solving this is understanding how the load behaves. For something like a conveyor belt, the torque, the twisting force, is pretty much constant. But for fans and pumps, the physics are a complete game changer. These are called the affinity laws. As you can see, the torque needed goes up with the square of the speed. But here's the kicker, the part that's truly brilliant. The power it uses goes up with the cube of the speed. You get that? This means if you can slow that fan down by just 20%, you slash its energy use by nearly half. So for our factory fan, the solution becomes crystal clear. You pick a simple, tough-as-nails induction motor for reliability, but you pair it with what's called a variable speed drive, or VSD, to control its speed precisely. By matching the motor's speed to exactly what's needed, you tap into that incredible cube law we just talked about and get massive, massive energy saving. That variable speed drive is the brain behind the brawn. It's the piece of tech that unlocks a motor's true potential for efficiency. So let's take a closer look. A VFD, which is often just called a VSD, is basically a power converter. You see, the speed of an AC motor is directly linked to the frequency of the electricity you feed it. So if you can control the frequency, you can control the speed.
And that's exactly what a VFD does. It works in 3 basic steps. First, it takes the standard AC power from the wall and converts it into DC power. Second, it cleans up and stabilizes that DC power using some capacitors. And finally, it uses these incredibly fast electronic switches to basically chop up that DC power and build a brand new, perfectly clean AC signal at whatever frequency and voltage it needs to run the motor at the perfect speed. And hey, besides speed control, VFDs have other huge benefits. Just look at this chart. If you start a big motor by just slamming it on, connecting it directly to the power line, it can draw this massive surge of electricity, often 6 to 8 times its normal running current. That puts a ton of stress on the motor and the whole electrical grid, but a VFD acts like a soft starter. It gently ramps up the speed by slowly increasing the frequency, which keeps that starting current incredibly low. And all of this leads to the bottom line. For jobs like pumps and fans that follow those amazing affinity laws, the potential energy savings from using a VFD can be more than 50%. That is a staggering number when you stop and think about just how many pumps and fans there are in the world. These kinds of savings, well, they haven't gone unnoticed. In fact, they have sparked a global push for higher and higher efficiency, completely revolutionizing motor technology as we know it. All around the world, governments have rolled out what are called minimum energy performance standards, and this has created a really clear roadmap for motor manufacturers, pushing them up this scale called the International Efficiency, or IE scale. We've gone from standard motors to high efficiency, then premium, and now super and even ultra premium efficiency motors are becoming the new norm. So to make these motors more efficient, engineers have to hunt down and eliminate every little bit of wasted energy. This chart shows you where those losses typically happen. The biggest culprits are electrical resistance in the copper windings and magnetic losses in the steel core. By using better materials and just plain smarter designs, engineers are constantly chipping away at these losses to climb that efficiency ladder. And you know what? The revolution isn't just about saving energy anymore. The future is about intelligence. Motors are now being built with sensors right inside them to watch things like temperature and vibration. By connecting them to the cloud, they become smart devices that can actually predict their own failures and tune their own performance. They're becoming key data points in the smart factories of the future. So, the humble electric motor, which was once just a simple, brute force machine, is evolving into this highly efficient, intelligent, data-rich hub. It really makes you wonder, with these unseen engines of everything getting smarter by the day, what are we going to build with them next?
Let's study more and like, share, and subscribe for such more content. And comment something you want to learn.